All right, so welcome to Chapter 15, Section 3. And what we would like to do is discuss the topic of independence of path and conservative vector fields. And we want to introduce an extremely important theorem known as the fundamental theorem of line integrals. But what I would need to do first is I need to introduce a topic. It's actually out of 15.2, but I just saved it to kind of for 15.3 just so I can tie it into the work that we're going to do here. But that is to introduce line integrals, right? So same line integrals, but we're going to introduce them in differential form. So all I need from you is to just recall that when we were working on using line integrals to calculate work, we saw that the line integral used to calculate work took on the following form. Now, what I'm going to do is we're gonna make just a couple assumptions. And then I'm going to show you what the differential form of this would look like. So if we just assume that your vector field, your force field, can be represented by the following vector. And of course, what we assume is that r of t is of the form x of t in the I direction plus y of t in the j direction. Then if you were to plug in what I had here for f, take the derivative of r and then the dot product, what you would find is that you could write this line integral in the following form. It would just simply be the line integral of some curve m dx plus n dy. But I want to make sure you understand we don't do a lot of proofs, and this is, but I do truly believe that you could follow me from this. Okay, so the question is, how can we get from the following to here, right? So this is where we began, and I'm going to show you how we can get from here to here, and I've already have it written for you. I just want to go through it really quickly. So, as you know, when you have your r of t, r prime is you're basically taking the derivative of r with respect to t, right? So that's just your definition of r prime of t. Now we know that from the previous page that we can assume that your force vector can be written in the following form. Now, dr dt, as you recall when you were taking the derivatives of those vector functions, that you would just take the derivative of the x component with respect to t, and then you would take the derivative of the y component with respect to t. So you can understand that dr dt, it can be thought of in the following form, right? dx dt I plus dy dt j. And that is exactly what you're seeing at this step. Now from here, I'm just performing the dot product, right? So it's the m times dx dt plus the n times the dy dt. And then what's happening is these dt's are canceling. And that is what leaves us with our differential form of the line integral. Now that is the recap, or not really recap, but that is all I needed to bring over from 15.2. What I want to do is I want to show you something that's it's quite remarkable, and I want and my hopes are that you can follow me through this without much of a problem. So the idea is, let's assume that you're seeking to find the work done by some force field, right? Maybe it's I don't know, a gravitational field. I don't know what it is, but it's some force field, and you want to find the work done by that field on a particle as it moves from one location to another location. So notice that our graphs here, this is all the same force field. Look at the little red arrows. See, there's the same forces acting. But notice that the path of that particle is going to vary, right? So in part A, the particle moves on a direct linear path from 0, 0 to 1, 1. Whereas in part B, the particle moves on this semi-parabolic path from 0, 0 to 1, 1, and an additional a new path for part C. But wait a minute. So what is the question? The question is, does the path matter? Right? Does the work being done by the force field on the particle, is the work going to be different depending on the path of the particle? So let's go ahead and note that this vector field is indeed a conservative vector field, right? So we're using that little test that we learned back in 15.1 to verify that this vector field is a conservative vector field. But this is a little bit of practice on dealing with line integrals again. So let's go ahead and note the first thing that we're going to have to tackle is look at the fact that your curve, the path, is given as a rectangular an equation, right? And not as a space curve, right? There's no parameter. So the first thing that we're going to need to do is take this y equals x and make sure we write it. We need to write it as a parametric space curve. So we need to write it as a function of t. The good news is this is we have some ability to, since there are many different parametric representations of the same curve, we have the ability to say something like, well, let's just let x equal t, right? Why does x equal t? Because you said so, because you defined it to be so. So, but the consequence of that, right? You don't get to state that x equals t and y equals. You don't get to fill in that part. Once you have certain degrees of freedom, in other words. So once you have defined x to be t, you need to plug in t for x to figure out what y is. Now, in this case, it just so happens that if x equals t, that y equals t. And that's it. That's all we need in order to form this parametric representation. So r of t is just going to be t in the I direction plus t in the j direction. Right? So easy enough. We're here. Let's go ahead and take r prime. So taking the derivative with respect to t. Now, there's going to be two other things that we're going to have to do, so we may as well, well, I'll tell you what. Let's go ahead and do the same thing we did here for b, for b. Okay, So in this case, I would let x equal t. I'll go ahead and do it here too. Let x equal t. Now that you've defined x to equal t, then we need to, the consequences of that is that y is going to equal what? It's going to equal the square root of t. And the consequences for the third curve is that if you let x equal t, then y is going to equal t cubed, right? So as soon as you plug t in, y is t cubed. As soon as you plug t in for x, y is the square root of t. Okay, now let's go ahead and write r of t. So r of t would be ti plus the square root of tj. R of t would be ti plus t cubed j. And while we're here, we can go ahead and take our derivatives. So r prime of t, that's going to be I plus, this one's going to be 3t squared, and this one is simply going to be 1/1/2. Well, let's just do it this way. You can write it as t to the power of a half. Take the derivative would be t to the power of -1/2. So I'll just go and write it that way. Okay. Now, at this stage, what we need to do is move back to our vector field. And we're going to have to represent our vector field in terms of parameter t as well. So what that means is, let's start with just a. So if x is t, I will be plugging in t here, t here. Y is t, I will be plugging in t here. So we need to be able to go ahead and substitute, and I'm going to just go ahead and do that right now. I'm going to start with just a because we're going to move to the next page. So f in that case would be 1/2 t times t I direction plus 1/4 t squared in the j direction. All right. So let's go ahead and set up our formula for work, and that is going to be the line integral. Now, in each of these cases, we have defined x to be t. So when you're looking at your xy points, if x equals t, then you only care about the x values, right? So this is going to be, since x equals t, t will be moving from 0 to 1 for each of those integrals. All right, but at this stage, you're going to need to go ahead and take the information here, and it's going to be f dot r prime, right? So let's go ahead and do that now. So remember, it was f was 1 1/2 t times t times I, so that's going to be 1/2 t squared in the I direction, and that's plus 1/4, plugging t in for x, that would be 1/4 t squared in the j direction. So now I got to dot that. And we're going to dot it with r prime, which in part A, r prime was just I plus j. So if you perform that dot product, this is the result. You get, the result is going to be 3/4 t squared. All right, integrate. That's going to be 1/4 t cubed, 0 to 1, which equals 1/4. Now, you'll notice that I made c extremely small down here, and I'll tell you why in just a second. But let's go ahead and go to part B. So remember, we have r prime as I plus t to the power of negative 1/2 j. We still need to be able to plug in the information, so I'm going to be plugging in t for x, and I'm going to be plugging in the square root of t for y. So let me come over here and set that up. So in this case, f, I'm just going to write it as f. Remember now it's f is a function of t, so it's f of x of t, y of t. But it's going to, f at this stage is going to take on the form of 1/2, it's x times y. Let me go back. Yeah, so it's x times y in the I direction. So t times square root of t is t to the half in the I direction, plus, and that's 1/4, and I believe that was x squared. So 1/4 t squared, the j direction. All right. So we can clean that up a little bit, but eventually what we're going to want to do is substitute that into our line integral. So t to the power of 1 times t to the power of 1/2 is t to the power of 3/2. And that's going to be plus 1/4 t squared in the j direction. Okay, so it's at this stage that we set up our line integral to calculate the work. Still going from 0 to 1. And I am going to save some space here. If you plug in f, which is above, with r prime of t, which is on the previous page, plug everything in and perform the dot product. This is the result that you would get. So after the dot product, you would have 5/8 t to the 3/2 dt. All right, and now we integrate and we substitute. So if you get done, so if you integrate, you would have 1/4, and that would be 1/4 t to the 5/2. You're moving from 0 to 1. Interesting. So if you go back and plug in, guess what your result would be? 1/4. In fact, if you were to do the same thing for part C, you would get a result of 1/4. Interesting. So it appears, right? This is just a tentative conclusion, but it appears that the work, right? Because we got the work that we calculated for part A, part B, part C was all 1/4, but it appears that the work that is being done by a conservative vector field is the same no matter what path the particle takes. And in fact, that is the case, and I will, in the next video, show you the result of all this. But you will have to, I know you're on the edge of your seat, but you'll have to wait.